Hello everybody, this is John. I'm a third-year PhD student in University of Michigan. Today I'm going to talk about one of our projects which we called OAI transmission rate control for the TCP servers. First of all, this project is a part of the Powder Renew project, which is one of the several nationwide wireless research testbeds funded by the Power Initiative. The Renew part mainly focuses on massive MIMO, and it's a collaboration between the University of Michigan, Rice University, and the Texas Southern University. The Renew partnered with the University of Utah to deploy a city-scale testbed in Salt Lake, Utah, and it's called Powder. We're going to see more about Powder towards the end of the presentation. So let's start with defining our problem context and what are we interested in. At the bottom of this slide, we see a generic mobile network architecture here. The left-hand side, we have an end user. The traffic goes through the base station, which is the radio access network here, and all the way up to the end server where we receive or get our application services. So often in this architecture, the bottleneck is identified as a radio access network because of a lot of physical phenomena going on there. And the bottleneck at the radio access networks called as last mile problem because it causes a lot of problems such as high latencies or jitter and everything. TCP, on the other hand, is a transport protocol. As just a quick refresher, it has mechanisms to adapt its sending and receiving rate for both ends of the communication channel. So in this case, because of the issues in the wireless network or the radio access network, the TCP algorithms might fail to accurately estimate or match their sending or transmitting rates at the end server. So in other words, it predicts the available capacity at the wireless link, and that results in underutilization of the available capacity. In this context, we would like to help the TCP server to adapt its sending rate more intelligently, more smartly. So we'd like to investigate the advantages of having an active TCP rate control between the base station and the TCP server. Our expectations by doing that is to improve the throughput or the capacity, so to achieve higher throughput for users and have lower latency. This is the high-level architecture or the high-level system design. So the main component we actually implemented in the OAI, OpenAirInterface radio component. So the main part here is we periodically report the downlink buffer usage per user or the buffer occupancy. And we sent this information all the way back to the end server. Our second component resides on the TCP server itself, which receives the feedback from the OAI base station. And using this information, it is more intelligently adapt its ascending window size, or in this case, we call it congestion window size, or CWND, based on the information we receive from the OAI. So it's a much more refined information, and it helps TCP server algorithm to predict the available capacity better. I would like to mention one important detail here. In this prototype, we actually assume that the end server IP addresses are known, and the base station, through the OAI code, can directly send the feedback to the end server. So this is often not the case in a practical deployment because base stations are not aware of IP addresses. Those are the responsibilities of the core network. There are the building blocks or components in a core network that maintains the IP address of both users and the servers or the machines that user accesses. So in a realistic setup, in a more realistic deployment, the core network should also involve in this messaging. Okay, so our first component, as I said, is located in the OAI radio part. And roughly we can divide the OAI code base into three main sections, whereas the OpenAir 1 directory is focusing on the physical layer stuff, the signaling and everything. On the top layer, we have OpenAir 3 directory, and this part is mainly responsible for communicating with the APC or the core network itself. The OpenAir 2, on the other hand, is mainly deals with the layer 2 resource allocation, the scheduling, and the MAC layer issues. So we made our modifications in the OpenAir 2, modified the scheduler code here, and at every scheduling time interval, our code gets the downlink buffer usage per user and calculate the running average, and then sends the feedback to the TCP server periodically every t millisecond. In this prototype, we chose t as 100 milliseconds. Our second component is located at the TCP server itself, and we call it OAI Enhanced Congestion Control. So this is nothing but an enhanced version of a well-known additive increase, multiplicative decrease congestion control algorithm. What we do here is we increase the congestion window size linearly until the buffer size exceeds the threshold here. The threshold is again configurable here. If the buffer feedback that we receive from the base station is greater than the threshold, then we're not going to increase the window any further, because that means the buffer is going way higher than we expected. So that means that might result in a congestion, and we don't want to increase the latency. So that's a good point. That should be a steady point. On the other hand, if we're receiving packet losses, then we're going to decrease our congestion control, the congestion window size, by half. We implemented our modified version of the congestion control in a framework called CCP, which is a brilliant study in SIGCOMM 18. Okay, now that brings us to the Powder testbed and the evaluation of the study. So Powder is very good because now we can define our experiments and our codes and everything in a profile, and we can define the components that we need. We can define the post-installation scripts and whatever necessary configurations our experiment is needed. And then all we need to do is instantiate that profile whenever we want to execute the experiment. So in this case, we use three components here. The left component is the user equipment. In the middle, we have the base station here, which OAI radio runs. And the right-hand side, we have the core network, or EPC here, which we use the next EPC, again, another open source project. So this is the full stack mobile networking, basically instantiated on the Powder servers. And whenever the machines are actually booted and all the configuration and the software are completed, we can now access them using SSH here, and we see all these three components here, again, the eNodeB, EPC, and the UE, and we can generate the traffic however we like it. Okay, let's talk about our evaluation environment here. As we said, we use the OpenAirInterface for realizing the radio access network. So as the base station, we use the OAI RF simulator operating at 10 megahertz. So for the core network, we used Next EPC, and as we talked, we did not have any modification for the core network yet, but as a future work, we definitely want to modify the core network to maintain this messaging protocol between base station. And for the user side, we used iPerf as a receiver. Again, no modification is needed on the user equipment. For the end server side, or the TCP server side, we used iPerf again, but this time it's using our customized TCP congestion control, which we called OAI Enhanced Additive Increase Multiplicative Decrease. Okay, let's take a look to the results now. So we tested our system here with either generating the constant traffic on one way, the downlink way, or transferring a different sized files, again, from the end server to the user equipment. So the results are more or less the same. So the figure shows just an instance for a file transfer of size 100 megabytes. So the top figure shows the default Linux congestion control, which is the cubic here. In most cases, the cubic is the default one. And at the bottom, we have our customized version of OAI enhanced congestion control. So as you can see, the problem with cubic is it can actually overestimate the wireless bottleneck capacity, particularly at 20, 40, and 70-second mark here. And this results in a packet loss, and thus a drastic reduction of the window size. On the other hand, the OAI-supported mechanism can start more aggressively to a point, and it actually maintain its sending rate with more stability. So ultimately, cubic takes approximately 5 more seconds extra to be able to transfer the whole file of size 100 megabytes in this case. Now we can provide up to 10% higher average throughput if we use the OAI enhanced version of the congestion control. And another good thing is that the average round trip time is also strictly better or lower for the proposed system. Okay, where do we go from here? So first of all, we want to expand the evaluation and make it more realistic by using real radio devices instead of simulators in the OpenAirInterface. And we would like to test it once we have the real radio devices. We're going to test more than one user at the same time, because the RF simulator can cause some issues with more than one user. So we're sort of stuck with one user in this case, in the prototype. And another thing is a potential direction here, as we just briefly discussed, is designing a messaging protocol for this whole OAI feedback mechanism. And this is going to involve the base station, core network, and the end server. And it will be much more practical, much more realistic, and deployable as well. And that's all for me. Thank you for listening.